In this video, I introduce maximum entropy inverse reinforcement learning. Inverse reinforcement learning is used to find the reward function underlying expert behavior for the optimal policy. Suppose the expert generates a trajectory zeta with a tilde under the expert policy. For the M trajectories, we define the feature counts f with a tilde. Here, this f is a feature vector. Suppose the reward function in Markov decision process is linear. So we can express this R as the product of this parameters theta and feature vector f. We cannot use the expert demonstration to calculate this theta and then this theta find the R, because the R is related to the optimal policy. That means we have to find the optimal policy, and then from optimal policy we determine this theta, and then we use the theta to find this reward R. And then use this R in the reinforcement learning to find the optimal policy. To do so, agent generates this trajectory zeta and his own policy. And then we define the probability distribution P over the trajectory using the reward on the trajectory and the partition function and the state transition probability together define this the probability distribution P. So our goal is to use the expert demonstration to train the model to find this P and make the entropy over this P maximum. That's what so-called maximum entropy principle. So we find this, find this P, make this entropy maximum so that the feature count and the agent policy equal to the feature count and the export policy. So to find the parameter theta, we need to define an objective function. We use this log P and the sum of the log P subject to this constraint. This is the feature count and the agent policy, and this is the feature count and the export policy. So if we view this P as the likelihood in the Bayesian theory, so we can use the expert demonstrations to find the maximum likelihood. That means we use the maximum likelihood estimate to find the maximum likelihood. So by using the gradient descent method to update the parameter theta, we need to calculate the gradient of the objective function is is equal to the feature counts and the export policy minus the feature count and the agent policy. So once we find this gradient of the object function, then we can update the theta until we get the converted the theta, and then we use the theta back to the reward formulation to calculate the reward. And then let's see how can we update the parameter theta. Now first, we need to calculate this partition function. Partition function is first we use the backward. That means we from this state Si under policy pi, we have so many choices to select the action A. At each action A, then now we from the backward, from the possible terminal state in a backward for path to calculate the to calculate this z step by step. That means we calculate the z over each trajectory, possible trajectory. And then now we put all the z over the pi over the action A together, we get the partition function. From this z at the action A, and then now we divide it by this z at the state Si, we get the local action probability, that means a policy. Use this policy in the forward to update the D at the state S for each time step. That means a signal travel from a current state, and each time we travel, until reach to the terminal state, we need to update the D at the Si at each time step for each trajectory. And then now once we get the D at each time step, we calculate sum over the time, we got the D at the state Si. And then now we use this D in this formulation to calculate the gradient of the object function L. This part again is the feature count and the export policy, and this is the feature count and the agent policy. So we use this one, we calculate the gradient, we use the gradient in the update to calculate the state. Once we get the convergence theta, then we use theta to calculate the R. And then now we use R in the reinforcement learning method to find the optimal policy. For more details, please check with this reference. Thank you. Bye.